Welcome to this demonstration of thermal heat transfer using Nastran In-CAD. We're going to talk about how to prevent machine failure due to thermal stress. Excessive heat causes various materials to expand at different rates, as is the case with the yogurt filling station and the Osgood industrial machine design seen here. The empty cups are sanitized, filled with fruit and yogurt. Several times per day the components are cleaned before running new products. Observe several nozzles used for cleaning in the graphics view. The heat that is generated during the wash cycle is hot enough to significantly expand the material used for the parts. Because we are dealing with food, the system is free of small components such as O-rings, and this requires tight tolerances to maintain pressure in the chamber. You can see in this cross-section we have a piston and sleeve made from two different materials. PEEK is used for the piston, which is a thermoplastic polymer, and stainless steel is used for the sleeve. The material properties come directly from the CAD design and contain all the information we need for the analysis. We have the conduction, specific heat, as well as thermal expansion coefficient. We are also given elastic modulus for thermal stress studies, which can be made temperature dependent for high fidelity. We only need to run half the model to gain accurate results for thermal and linear static studies. There are symmetry restraint options available to make it fast and easy to define the behavior. There are two loads to apply in this scenario. First, the initial condition will be set to room temperature, or 294 degrees Kelvin. Secondly, we are going to heat the components to 350 degrees Kelvin or 170 degrees Fahrenheit to emulate the wash cycle for the machine. Nastran In-CAD provides automatic as well as full manual control over the contact conditions between the components. In this case, there is a small gap between the piston and sleeve. We want to allow the two parts to slide against each other. And finally, let's mesh or divide the parts into several pieces to be analyzed, and run the study. Again, we want to understand more about the thermal expansion due to the wash cycle. What kind of impact will it have on the normal operation of the yogurt filling station? Let's begin with displacement in the X direction. We can see right away there is some expansion on the piston right above the sleeve, an early indication the parts are contacting each other. Let's also take a look at the stress plot. Here we can observe the impact between the piston and the sleeve after contact has occurred. It is apparent that the PEEK material for the piston is expanding much faster than the sleeve. Since we are analyzing these components in the comfort of the CAD design software, we can make any modifications to the geometry and simply rerun the study. For example, we will change the diameter of the main bore on the sleeve. Back in the assembly, it is simply a matter of updating the mesh and rerun the study. This workflow encourages design validation early from concept to release for manufacturing, when making modifications is most affordable to do so. The results may improve with the change, but the reality is the wash cycle requires the components to cool off before running the machine. Let's dive deeper into each of the parts to fully understand the cooling process. With the sleeve open by itself, we will begin by running the thermal expansion scenario. We can then determine deflection quickly without the interaction from other parts. Once again, we will set up the initial room temperature of the components and apply the heat from the wash cycle. In the rest of the linear static studies, we have already applied the symmetry constraint and two other constraints to prevent the part from moving in the X or Y direction. First, we will look at the displacement in the X direction. The legend provides the range of displacement for minimum and maximum, but we may want to know the displacement for specific areas on the part. The probe tool will help to check the inner bore of the sleeve. It looks like there is not a lot of expansion for the stainless steel material. Based on the results so far, we know we have to wait for the parts to cool off, but how long exactly does it take? This temperature for the initial condition is starting at 350 degrees Kelvin, and we have a convection boundary condition that has already started. In here we can specify the air temperature surrounding the filler, and it could be time dependent. In this case, the washer may still be a little warm for a few minutes, and we want to take that into account. The convection coefficient can also be temperature dependent. This is a nonlinear transient study that we're running over a 50-minute cooling period. After running the study, we are able to determine the maximum temperature of the sleeve at every minute of this range in time. The beauty of running nonlinear studies is the ability to view the results as it's running. Not only can we view the temperature results, we can also take a look at the maximum temperature over time. This is a huge time saver for studies that take longer to run. We are able to take notes early before the analysis is finished, or stop the calculation at will and make changes to the setup if necessary. The solver is finished. Taking a look at the graph, the stainless steel sleeve quickly drops in temperature within 15 minutes. Animations can also help to observe the behavior of the cooling process. Nastran In-CAD keeps track of the result plots for all 50 time steps during the calculation for visualization and data. Let's do the same thing for the piston since it's manufactured from a different material. Once again, we will set up a thermal expansion study to determine the displacement of the component by itself. We are starting at a room temperature and heating the part up to 350 degrees Kelvin. Let's also take advantage of multiple cases. Nastran In-CAD enables the ability to reuse boundary conditions with a drag and drop. We will run another scenario with a minimum body temperature of 310 degrees Kelvin. After running this study, we will know how much the diameter of the piston is expanding. This time we don't need the probe tool since the minimum and maximum displacement values are on the outside of the piston body. All we need is a plot that shows the displacement in the z direction. We are getting a much larger expansion on the piston as opposed to the sleeve, indicating the problem with using parts made from widely different materials. Let's also take a look at the displacement plot for the second case with 310 degrees. Now these results are acceptable for running the machine. Our goal may be to cool the components to under 310 degrees prior to operation. Now let's find out how long it takes to cool the piston. Once again, we are starting at the peak temperature of 350 degrees Kelvin. The convection is the same as the sleeve study. As you have seen with the calculation on the sleeve, we can monitor the cooling behavior of the piston as well. As expected, we are observing the convection at work on the outside of the component. After the study is complete, we will know how long it takes to cool the piston, and we will also have the results that can be used in a thermal expansion study. The graph shows that it takes much longer to cool the peak material for the piston. It takes a full hour to reach 303 degrees Kelvin. We already ran a thermal expansion study using body temperature. Let's run that same type of study again, except this time we will use the actual non-uniform temperature from all the nodes as our load condition. This is a great way to gain high-fidelity results for the displacement of the piston. Notice we can even choose from any of the 50 time steps from the nonlinear study. Once again, multiple cases can be used here to check the displacement at various times during the cooling period. We can see that the maximum displacement is well within reason for normal operation of the yogurt filler at this temperature. We now have a good understanding of the behavior of the components after the wash cycle is complete. Based on these results, we can make educated decisions on the length of time necessary to cool the components. We may recommend 45 minutes before normal operation begins. Since the washer runs in zones, it is best to start with the yogurt filler and move on to the rest of the machine for cleaning, providing plenty of time to cool. Back in the assembly, there is one other scenario worth looking into. At times, the food that is used in the filler may be heated. If that is the case, we should consider running this study. This time, the heat source is applied to the faces in the chamber, including the bottom faces of the piston. We will use a temperature since the food is constantly being moved in and out of the sleeve. The convection condition on the outside of the piston and sleeve will remain similar to the other studies at room temperature. Let's have a look at temperature. As you would expect, the stainless steel is conducting the heat much faster than the peak material. This could be an issue if it's not being distributed as much as we'd like. Once again, it's worth running a thermal stress study to ensure that these temperatures are not going to be a problem. We will set the initial condition to room temperature and heat the components up using the results that we just saw from the thermal study. After running the analysis, we will find out if there are any geometric changes necessary for running warm food products. Taking a look at the stress plot, it does not look like we are going to have a problem with warm food. If a design change is necessary, remember that we are doing this right in the CAD design environment. Simply make a change to any dimension or add new features to the model. Run the updated design and find out if your idea works or not. This is a great workflow for designers as well as the analyst who needs a robust solver for advanced study types. Thermal studies are just one of many types of calculations Nastran In-CAD is capable of. Be sure to watch more of our demonstrations showcasing nonlinear buckling and dynamic simulations for industrial machine designers. Autodesk Nastran In-CAD is a robust, easy-to-use tool that is fully embedded in Inventor and SolidWorks. It is your trusted solution for getting the high-fidelity results that you are looking for, and it is the future of making things.